In the second half of this lecture, we're going to focus on the different parts of the ear and how they help us both hear and maintain equilibrium or balance. So we hear the world through our ear, and our ear has three main parts: the outer ear, which the job of the outer ear is essentially to get sound to the middle ear. And the middle ear, and the job of the middle ear is to amplify sounds so that it can be registered by the inner ear, and the inner ear takes the sounds that reach it and transform them into action potentials that can then go down the nerves and to your brain, and so that your brain can actually register what's going on. So this also makes sense because your inner ear, this really important part that helps transform sounds into neural signals. It also helps maintain your balance. This is really far into your head. And so your outer ear can get damaged, and your middle ear can kind of get damaged without actually any real damage happening to either your hearing or your balance, which are both really important senses. So it makes sense that this is kind of the orientation of your ear. So this is really well protected. So your outer ear is made up of two parts: the ear canal and the auricle, which is the outer part of your ear. There's a lot of duplicate names, and so I'll try to make it clear what names we want you to know. And so the auricle is the outer part of your ear, the ear that you can see. And this acts to funnel noise. It acts to collect noise from around the ear and bring it down into the ear canal, which also helps funnel sound into this part of the middle ear. And again, the job of the outer ear is to both funnel noise and also to kind of remove that from the outside of your head and put it really inside your head. And so it's really kind of buried. And we have two ears. Most people have two ears. And the distance between ears helps locate sound. And so we can tell roughly if a sound is on the right side of our head or on the left side of our head, depending upon what ear it's coming into, and right in front of us or right behind us, and so on. Makes sense, pretty basic. The middle ear is responsible for taking those vibrations that they are registered by the outer ear and really amplifying them for the inner ear. And so it's made up of two parts. One, the eardrum or tympanic membrane, and this is one of those that we'd like you to know both names. So the eardrum, it vibrates with waves, and so it's a membrane that vibrates when um, when sound hits it. And then we are talking about three different bones called the incus, malleus, and stapes, which are also called the anvil, hammer, and stirrup. So they have really fun names and a little etymology here. Ossi means bone, and cols means little. Well, we also thought about this with molecules and ossi, also like ossification or ossified. Um, so they're little bones. They're the smallest bones in your body. And it's these three. You don't need to know exactly the name of the three, but just that they are a trio of bones and they amplify sound. And so I know that this looks slightly strange, but I thought it was really important that we have this little video that shows how this amplification of sound works. And before we show the video, I want to talk a little bit about why it's important that we amplify sound. And so, though we said that it is faster for sound to move through water than it is through air, it's also more difficult for it to move. So it doesn't necessarily go as far. And so because the inner ear deals primarily in fluid that you have in your cochlea, it's important that you amplify sound in order from the air to get here. And so that's why we have this amplification in the inner ear, in the middle ear.
Tympanic membrane separates the outer ear from the middle ear. Sound waves cause it to vibrate. The three tiny bones of the middle ear are the hammer or malleus, anvil or incus, and stapes or stirrup. These bones pick up the vibrations from the tympanic membrane and transmit them to the inner ear. The eustachian.
Okay, so I know again it looks a little weird, but I think it's important to help you see how these work. So the inner ear again has the job of converting pressure into signals that your brain can understand, and we're going to talk a little bit more about how it does that. But first, it has a couple of main parts. First, you have the cochlea, which is here. It looks like a snail shell. Cochlea is Latin for snail. And it converts vibrations into neural messages. We're going to talk about how it does it in a second. And then we have the cochlear nerve, which carries messages to the brain. This is very close to, so for a while, it's the vestibular cochlear nerve. A vestibular system is the system that helps you keep balance, which we're going to talk about in a little bit. But in this instance, we're just going to talk about it as a cochlear nerve, so it transmits sound information from the cochlea all the way to the brain. We're also thinking about the eustachian tube, which just normalizes the pressure inside the head to the outside of the head. So this is the part of your ear that deals with if you are in a plane and your ears pop because the pressure changes. This is because your eustachian tube is help balancing those the air outside your ear to the air inside your head. And so this is also, if you can see, it goes down. And so if you were to kind of go down, this connects to your nose and throat. And so this is why, for instance, if you yawn, your ears will not pop on planes. Same if you chew gum. So that makes sense why the eustachian tube is involved in that process. So, to talk about how our ears distinguish sound, because it's important that our ears don't just hear sound, but then they actually tell us something about the sound, because there's major differences between like an airplane taking off versus a bat versus music versus your mom's voice. They all sound really different. And so, how do we identify those? Um, so if this is the cochlea, if you were to unroll it, so this is the cochlea, if you were to unroll it, it has these different layers. I'm not going to talk about all of them. We're just going to talk about the basilar membrane, which is the middle one here, which has the organ of Corti. And so we're going to talk first about inside the organ of Corti, we have these hair cells. And the hair cells look like this. They look like they have hair on top of them. And so they move dependent upon how quickly and how hard the vibration hits them. And so they move more with louder sounds, and they have little itty bitty connections that you can't see between these. And those connections can actually snap if they move so fast or so much. And this is actually what causes hearing loss from listening to loud sounds. And you also can't actually get these connections back. Once they're broken, they're broken. So that's why it's so important to use hearing protection. This is my public service announcement for the day. So louder sounds mean more frequent action potentials. So this hair cell, when the hairs appear that are in your organ of Corti vibrate, then they open sodium channels, and those sodium channels, potassium channels, and those potassium channels depolarize the cell and ends up with mechanical electrical conduction, which basically means that it sends an action potential to your brain down the vestibular cochlear nerve, as we talked about. So louder sounds mean more frequent action potentials. Louder sounds mean that your hair cells move more. And then we can also think about the basilar membrane. And so we've got inside the cochlea, if you unroll it, say this is the basilar membrane, it's right next to the organ of Corti. So the organ of Corti is helping you figure out how loud sounds are. The basilar membrane is telling you the pitch of sounds. And so it's like the basilar membrane has a bunch of strings on it. And so the strings at this end, at the base, are pretty short and stiff. And the further you go, they are longer and less stiff. And so if we think about what we talked about in terms of sound on strings, you can imagine that higher frequency sounds are down here at the base, and lower frequency sounds are way down here because these are long strings, which we know is correlated to low notes, and also they're pretty loose. And so lower frequencies have long wavelengths that goes all the way down here, and high frequencies have short wavelengths and they don't travel as far. And so this information, since it's right on top of the organ of Corti, ends up communicating to the hair cells as well. And so the hair cells are able to communicate that information down the cochlear nerve vestibular cochlear nerve. And so you have these two pieces of information. Just to review, you have how loud something is, which is directly by the hair cells, how much a hair cell moves, how much these hairs move, and is directly related to the number of action potentials that are sent. And so um, that makes a lot of sense, because if a sound is really loud, it's like, pay attention to me. If you're at a rock concert, then like, pay attention to me. So lots of action potentials. And then you also have the basilar membrane, which also makes sense. If you have a high pitched sound, it doesn't go very far. It has a really short wavelength. If you have a low pitched sound, it goes really far. It has a long wavelength and a lower frequency. And so both of these pieces of information then travel down the vestibular cochlear nerve and eventually arrive at your brain when you can tell something is a low or high sound and how loud it is. So just to review one more time, if you have a nice wave here, it starts interacting with the auricle, say outside of the ear, and then it travels down the ear canal, and it travels down so partially so that your inner parts of your ear are protected. It strikes the tympanic membrane or the eardrum, and as it does so, it hits the ossicles, those tiny little bones, which amplify the sound, which is important because it's then going to travel through liquid in the cochlea, and that is going to translate to the cochlear nerve. And inside the cochlea, we have the organocorti, as well as the basilar membrane, which tell us about volume and frequency, respectively. So in the very last bit of this lecture, we're going to talk about how the ear helps us maintain balance.